Hello everyone. We're starting some problem solving in thermodynamics. So the first type of problem that I'm going to do is work on a gas and how we can use first law of thermodynamics to gain some more information about that. Okay. So when we talk about work for a process, when we talk about work in thermodynamics of a gas, for a gas, we usually present the process in a PV diagram, like so. So like point A for here represents that A represents state A, and in state A you will have properties like pressure, volume of the gas, and you have, of course, how many molecules there are. It's a number of molecules, and then you can have temperature when the gas is there. So if ideal gas, which is not here, okay, if the gas is ideal gas, so say this is some kind of container and this is the ideal gas, and if ideal gas, then you have what is called equation of state of ideal gas. Then these guys are related by equation of state. Then you will have a PA VA equals N, number of molecules, times Boltzmann constant times TA. But these things are there, but for our problem this may not be the case. Okay, so don't assume this is the case and you have access to temperature or number of molecules. We don't have access to these in this problem. Sometimes the students get kind of sidetracked with that. I know, I just wanted you to not get sidetracked. Okay, so A is that. So these are given. At B, B means state B. B means state B, and state means these properties. Okay, state B, and then you have a PB and VB, and you have number of molecules N and TB, which are not known. Okay, at C, C means state C, and PC, VC, and then corresponding you'll have N and TC. These are not known and not necessary to know here. Okay, so what's happening A to B is pressure is constant. At B to C, volume is constant, and over here is linearly changing. So there's a pressure is a function of volume here. Okay. So what is the definition of work in this situation? Definition of work in this system. Well, this is gas, right? So if you have a gas and you have a piston here, and so you kind of maintain some volume V and some pressure P on it in equilibrium. So when you push, so there's some force here, let's call that force from outside, and this area of cross section is A. So inside there's a stress, we call it pressure P. So you can change the force, and so when you push on it, say incrementally, you change the volume by dV while the volume was V. So the V went from V to V plus dV, with the dV less than 0 for compression, and P remain almost P. Okay, then the work on gas is defined to be minus P dV. Why minus? Because dV is 0. So you have done the work, so you increase the energy went up. So delta E in this process is going to be, some heat may be involved through that, so this will be some Q. So let's call it a small process dE, and usually dQ is, you cut it because it's not a real differential. So it's a process dependent. So let's call this dQ. Then I'm not going to go into detail of what the Q is right now. So small dQ and plus dW, use the dW, plus, you are going to have something has to do with number of particles and types of particles, right? So this is 0 here because I'm not changing the number of particles in this gas. I'm not changing number of particles. And we're not talking about this, so we're talking about that, and that's equal to minus P dV. All right, so minus P dV. So the work in any process, if I go like, let's do A, so AB process, that will be minus integral P dV. And so this is the integration variable V, so it's going to go from VA to VB. Now P on this process is constant, so it's going to just come out minus VA to VB, and this just pick PA, same thing, PA is equal to PB is 1, and then you have a dV, and so this comes out of the integral, and when you do this integral minus PA VB minus VA. So you can see that this is going to be positive, this is positive. So once you work it out, this is 10 to the power 5, and then this is 4 minus 2 minus 10 to the power 5, 4 minus 2, this is 4, and this is 2, so expands. So actually when the gas expands, it loses energy. So look at this, it's losing energy, minus 2 times 10 to the power 5. So this is in Pascal and this is meter cube. It's a Pascal meter cube, and this is all SI units. You can show that this is same as joules. So this is equal to minus 2 times 10 to the power 5 joules. So that's the answer for A. Let's do B over here. So in the B, volume is not changing anywhere. No place volume D, all dV is 0. On BC, dV equal to 0 at all places, right? So when you integrate P dV, VB VC, WBC, that's going to become 0. So that's a straightforward integral. How about to C? Let me erase and then come to the C. Okay, so I'll just write down what we found. AB is minus 2 times 10 to the power 5 joules. WBC equals to 0, and let's look at WCA. Okay. So we are doing C, and you want to know on this. This is the equation of a straight line, and we need to know P as a function of V on that. So at any point, say this some arbitrary point P, PV, so P minus PA PC minus PA, so that's the slope, and this so V minus VA minus VC minus VA, so so this is going to be P equals to PA plus PC minus PA over VC minus VA V minus VA. And so this just divide everything by P over 10 to the power 5, just to keep the numbers small, and PC is 3, PA is 1, and VC is 4, VC is 4, and VA is 2, V minus 2, so this is like 1 plus half V minus 2, right? No, not half, this 1, this is 2, and this is 2, so they'll cancel, so this is V minus 1. So P is actually 10 to the power 5 V minus 1. Okay, so now we want to do WCA minus go from VC to VA and P dV. So P is this guy here, P is this guy here, so minus VC is 4, 4 to 2, and P is 10 to the power 5 V minus 1 dV. So just come out minus 10 to the power 5, and anyway V is square over 2 minus V 4 2. So let's see, minus 10 to the power 5, 2 square over 2 minus 2 minus 4 square over 2 plus 4. So this becomes 2, this will cancel that guy, so this cancels that guy, and this is minus, this becomes minus, this is 8, and so this whole thing becomes minus 4, so this is equal to plus 4 times 10 to the power 5 Pascal meter cube, which is same as 4 times 10 to the power 5 joules. So over here you have to do positive work. Over here you do negative work. So AB, this is BC, and this is CA. This number is CA. Okay, how about D? So work in any process is this integral, and you can break up the integral into sub-process, you know, if you can break up and can do the integral in steps like we have done over here. So it's going to be just add up from A and a B and a C. We can just add those up, so this will be the A to B to C to A, just WAB plus WBC plus WCA, just add them up. So this is going to be minus 2 plus 0 plus 4 times 10 to the power 5 joules. And so when you add them up, it becomes plus 2 times 10 to the power 5 joules. So that's the answer for the entire thing, which means I actually work was done into the system. So WCA turned out to be plus 4 times 10 to the power 5 joules, and W cycle turned out to be 2 times 10 to the power 5 joules, right? Okay, so let me erase and try to answer 2 and 3. They're the important ones. Okay, 2. Why did we do all this work to find these answers? Well, we need to understand what's going on, and that's 2 and 3 are likes. So how much energy changed during this cycle? So if I have my state A, then it has some energy EA. When I'm in state A again, it has the same energy EA. So the change in energy in any cycle will be equal to EA minus EA equal to 0. So energy actually just depends on the state, right? So if I give you pressure, volume, pressure A, volume A, temperature A, and how many molecules are there, if I have given you this, I've given the state of the gas, and from there, unless these values change, your energy is not going to change. Okay, in an ideal gas, even more strict. It only depends on energy, only depends on the temperature. Okay, in ideal gas, but we don't know this ideal gas, and it says not necessarily ideal gas, so we can't take that for granted. So it all there are 4 things that determines a state of a regular gas, and from there we can, of course, you can say N over V can be like a density, number density, right? Number of molecules per unit volume. So you could combine these two and say N over V. I want to write in terms of N over V. Okay, so this is very easy. 2 is very easy. How about 3? What can you say about heat during the full cycle? Well, what went on, so that's the first law. First law will say that in any process, if I take any process, I know it says 0 energy change. Any energy change that could happen can come about through mechanism of heat, mechanism of work, and mechanism of changing particles, number and types of particles. So this is the first law, and this includes, chemical reaction can change number type particles. For us here, this is not happening. So just this, right? So now we say that in the cycle, so over the cycle, this part is 0, but so we want to say, what can I say about this guy? This must equal to that, but this is equal to plus 2 times 10 to the power 5 joules. We just found out. So this is the part D. We found that out, part D. So this Q has to be negative of that, which means energy must have flown out as heat. So the Q is minus 2 times 10 to the power 5 joules. So whatever work we had to do to compress the gas in this process, mostly this process, okay, what are the work I had to do this, and what are positive negative work that come out of this, these two together had to be balanced by heat flow and heat in the system, right? So this is the amount of heat flow in the system. So let's dig a little deeper and see each process, what could have gone on. Okay. So what did we do? We had gas at A. This was A, and then we went to B. Kind of doubled it, right? Doubled it, and then we stayed there. We compressed it. So maybe over here I won't let the volume change. So over here So from here to here, I think I have to heat it up, right? So that pressure so this is at B. Pressure went up, but the volume delta V remained the same, B to C. So how can pressure go up and volume is the same? I have probably had to put some heat in. So in here I put heat in, over here you can see that it pressure remains the same, the volume doubled up. That means I need to cool it. Q went out, so I expanded it. No, actually I need to put heat in, heat in here too. I expanded it, but pressure same, which means I need to heat it, right? I heated it. Q went in. And the last one that happened is this one had to be cooled. So back to A, I had to cool it here. And so over here the heat went out. So amount of heat that went out here overwhelmed this heat that went in, and the net amount Q out will be negative, and Q in 1 and Q in 2, Q in plus Q in 2. These, when you add all of these up with this negative, that's what we got. Okay. So we are going to do some more problems like this in the next videos. As you do more of these problems, you're going to start to get more feel for how to use this equation. And a lot of times people learn these equations piecemeal. They learn how to do this, but I would say whenever you're learning how to do this, try to put in the context of this whole thing, whether you're learning at some other places. Okay, just to remind you to hit the like button. It helps us increase the circulation of the video, and check out my website www.physicsbootcamp.org. Now if you want me to do some problem or something like that, you want me to ask questions, you can leave comments below and then I will try to address them. Thank you. Take care. Bye.